Okay, let's dive in. If you've been watching the Coco leaderboards, I mean, for the last year and a half or so, you know the story.
Oh, yeah.
It's basically been the Dino Show. The detection transformer with improved denoising anchor boxes. I mean, Dino has just become the absolute baseline to beat.
It is the standard.
Yeah.
And for a very good reason. Dino really did solve a lot of those early convergence problems from the original DETR.
With things like contrastive denoising.
Exactly. And the mixed query selection. It just made transformer-based detection, practical.
Right. But, and this is where things get really interesting, especially if you're someone who actually stares at loss curves all day. A new paper is suggesting that Dino, and frankly almost every DTR variant out there, has this fundamental structural instability.
Mm.
And we're not talking about just tweaking hyperparameters. This is a flaw in the core matching logic itself.
It's a really fascinating diagnosis. The paper's called Detection Transformer with Stable Matching. We'll probably call it stable,
Stable Dino, yeah.
It's from Tsinghua University in IDEA, and what's so compelling is that they're not proposing some massive new architecture.
No new attention mechanism, no extra encoder layers.
None of that. They've just identified this subtle but really critical conflict in how these models learn during training. They have a great name for it, the multi-optimization path problem.
Multi-optimization path.
Yeah.
Sounds very control theory. So that's our mission for this deep dive. We're going to unpack that problem.
Yep.
We'll look at why that one-to-one matching strategy might be fighting itself, how Stable Dino fixes it mathematically, and of course why this all leads to a new state-of-the-art on Coco.
And to really get the fix, you have to get the flaw. And it all comes down to the thing that defines DETR models, the bipartite matching.
Right. So for anyone listening who's more from the, say, old-school RCNN world,
Right.
in a traditional detector, you have anchors, lots of anchors.
Right, one-to-many assignment.
Exactly. You might assign multiple anchors to one ground truth object.
Yeah.
But DETR is strict. It uses the Hungarian algorithm to force a one-to-one match. One ground truth, one prediction. That's it.
Correct. And that exclusivity, that's where the problem really starts. The authors lay out this perfect theoretical scenario in the paper. It's figure 2. Imagine you have one ground truth object, a car.
Okay.
And your model, it's mid-training, so it's not perfect. It gives you 2 different imperfect predictions for that same car. We can call them prediction A and prediction B.
Okay, got it. So what do these boxes look like?
Prediction A is, let's call it the spatially accurate, semantically weak one. It has a really high IOU with the actual car. The box is nice and tight.
Okay, good localization.
But the classification score is terrible. The model's only, say, 20% sure it's even a car.
So good box, no confidence. What about prediction B?
Prediction B is the exact inverse. It has a super high classification score. The model's just screaming CAR, but the bounding box is, well, it's sloppy, really low IOU.
So it's caught maybe a bumper in a lot of the road.
Precisely.
So we have a shy genius and a confident idiot.
That is a perfect way to put it, yes. Now, here's the problem. The Hungarian algorithm has to pick one of them to be the positive sample.
And it does that based on a matching cost, right? Which is a mix of position cost and classification cost.
Exactly. And because you're training with SGD, the network weights are always in flux.
They're fluctuating.
Right. So in one epoch, maybe in just one decoder layer, the current state of the weights makes the matching cost favor prediction A. The spatial cost wins out, and the shy genius gets matched.
And when that happens, the gradient descent signal tells the network, great work, you nailed the location, keep doing that. It optimizes for spatial accuracy.
That is optimization path 1. But then, a few iterations later, or maybe in the very next decoder layer, the weights shift just a tiny bit. And now, that super high classification score from prediction B, the confident idiot, it lowers the total matching cost just enough.
And it wins the match.
It wins. And now the gradient signal completely flips. It tells the network, awesome job, you were so confident. Keep optimizing for high confidence, even if your box is terrible.
Wow. Okay, so that's the multi-optimization path. The model is just oscillating. 1 minute it's told to prefer high IOU, the next it's told to prefer a high classification score.
It's getting conflicting supervision. It's being told that the confident idiot is just as valid a target as the shy genius, all depending on the noise of that training step.
That has to just wreak havoc on convergence. You're basically confusing the model about what its actual goal is.
It creates a really jagged optimization landscape, and they show this. They actually track the assignments across the 6 decoder layers in a Dino model.
And it's messy, I assume.
It's all over the place. A single ground truth object might be matched to query 45 in layer 1, then jump to query 12 in layer 2, and then query 99 in layer 3. It's totally unstable.
Ah, the unstable matching from the title. The model can't even decide which query is responsible for the object from one layer to the next.
And this is really a problem that's unique to one-to-one matching. In a one-to-many system like YOLO, both of those predictions would probably be treated as positives.
Right, the model would learn from both at the same time. Good boxes are good, and high confidence is good.
But DETR forces this binary choice, and that just magnifies the conflict.
Okay, so the solution. Stable Dino's approach seems almost deceptively simple. They hit it from 3 sides: the loss, the matching cost, and a little tweak to the architecture. Let's start with the loss.
This, I think, is the main contribution. It's the position-supervised loss.
So standard Dino uses focal loss for classification. And in focal loss, if you're the chosen positive sample, your target is 100% confidence.
Right, and that's the trap. Because if the matcher picks prediction B, our confident idiot, the focal loss says, yes, perfect, push that score to 1.0, you're doing great.
It actually reinforces the bad localization.
It totally does. So stable Dino just changes the target. In equation 3 of the paper, they literally replace the binary target 1 with a function of the positional metric. The new classification target is effectively the IOU score itself.
Wait, say that again. So if my confident idiot prediction high score, but only say 0.2 IOU if that gets matched.
The loss function hammers it. The target is no longer 1.0, it's 0.2. So even though your model predicted, say, 0.9, the loss function says, nope, you should have predicted 0.2 because your box is garbage.
That is brilliant. You're forcing the classification head to be entirely dependent on the regression head.
It has to be.
You're only allowed to be confident if your geometry is good.
Exactly. It just unifies the optimization paths. There's no longer a reward for bad box plus high confidence. The only way to get a low loss is to have a good box and a high score that actually reflects the quality of that box.
Okay, but that brings up a question immediately. If you change the loss to punish the confident idiot, don't you also have to stop the Hungarian matcher from picking it in the first place?
Yes, otherwise they're just fighting each other.
The matcher and the loss would be at odds.
You are exactly right. And that is the second major contribution, the position-modulated matching cost. You have to align the assignment logic with the supervision logic.
So what does that look like mathematically?
In the standard matching cost, you have a term for the predicted probability. Let's call it a $5.
A higher $B makes the cost lower, makes a match more likely.
Right. Stable Dino changes that term. Instead of just using $P, they use $P multiplied by a positional factor, basically times the function of the IOU.
So you're modulating the score.
Precisely. They use a rescaled GIOU, so the term becomes something like $P spat do U.
And that just kills prediction B on the spot. It has a high P-dollars, but its IOU is tiny, so its modulated score plummets, the cost goes way up.
And the Hungarian algorithm just ignores it. It filters out those predictions that are just, hallucinating confidence without any spatial grounding.
It cleans up the matching process.
It does. And by ensuring only high-quality boxes are even really considered for matching, the whole assignment process stabilizes across all the decoder layers. The results on this are super clear. They plot these unstable scores.
Here's how often the assignment flips between layers.
Yeah. And stable Dino just crushes Dino. The reduction in instability, especially in those early decoder layers, is dramatic.
Okay, so we've fixed the core logic, but there's a third piece here. Dense memory fusion. This seems to tackle a different problem, which is convergence speed.
It does. This is about building a better bridge between the backbone network and the transformer encoder.
Let's give some context here. In a normal DETR, you have your backbone, like a ResNet, extracting features. Then those features get fed into the transformer encoder to mix global context, but that encoder starts from scratch.
Right. At epoch 0, your backbone, which is pre-trained on ImageNet, it already knows what a cat looks like, has rich features. But the encoder is a blank slate. It's a bottleneck, and it takes a while for it to learn how to properly use those great backbone features.
So dense memory fusion is a kind of shortcut.
I'd call it an augmentation. The authors basically propose fusing the backbone features directly into the decoder, kind of bypassing the encoder's initial learning curve.
So how do they do it?
They take the encoder's output features from the different pyramid levels. They also take the multi-scale features straight from the backbone. Then they just concatenate them, run them through a linear layer to get the dimensions right.
And feed that whole fused sequence into the decoder?
Exactly. So the decoder gets the processed, contextualized info from the encoder, but it also gets the raw, high-quality semantic info directly from the backbone.
And the visualizations in the paper, figure 9, they're pretty striking.
They really are. They show the attention sampling points in the very first epoch. For vanilla Dino, the points are just scattered everywhere. The model is kind of lost. With dense memory fusion, it's already focusing on the object boundaries immediately.
It's just leveraging that ImageNet pre-training so much more effectively from the get-go.
And crucially, this whole operation is cheap. It's a concatenation and a linear projection. It adds almost no computational overhead.
All right, let's talk results. The payoff, we've fixed the logic, we've sped up convergence. Does it actually move the needle on CoCo?
It moves it a lot. Let's start with the Resonant 50 backbone. On the standard 1x schedule, that's only 12 epochs of training.
Okay.
Stable Dino hits 50.4 AP.
And for context, the original Dino was about 49.0 AP on that same schedule. So that's a plus 1.4 AP jump. I mean, in today's object detection world where people fight for 0.2, 0.3 AP, 1.4 is a generational leap.
It's a huge deal, and it scales up. On a 2x schedule, 24 epochs, it hits 51.5 AP. But the real headline result is what happens with pre-training.
The Objects 365 experiment.
Yes. They take a Swin-large backbone, pre-train it on that massive Objects 365 dataset, and then fine-tune on CoCo.
And the number is?
Stable Dino reaches 63.8 AP on the CoCo test dev set.
63.8. That's a new record for that setting, isn't it?
It is. It sets a whole new benchmark for what this kind of transformer architecture can do.
And what's so impressive is that this isn't some trick that only works for Dino.
Yeah.
They applied these stable principles to a bunch of other architectures.
Right. They tested it everywhere. On deformable DTR, on DAB DTR, on HDTR, and in every single case, the performance just went up.
By how much?
Stable deformable DTR gained about 1.3 AP. Stable DAB DTR gained 1.0 AP. It just works.
They even did it for segmentation with Mask Dino.
Yep, stable Mask Dino. And it beat the baseline by 0.7 mask AP. It really strongly suggests this multi-optimization path problem isn't just some quirk of Dino, it's an inherent flaw in the entire one-to-one matching idea.
Which brings me to the analysis section of the paper, which I found fascinating. They talk about the classification score being a reluctant design.
Yes, this is a great point. If you go back to the original DETR paper, using the classification score and the matching cost was a necessity. If you didn't have it, training would just collapse.
Because without it, how does the model know which query to assign? The queries are just learnable slots, so in the early stages, you need that class score to act as a kind of signature.
Exactly. You need that little semantic hint to stabilize the assignment. But, and here's the irony, by adding the class score to solve assignment instability, they accidentally created optimization instability.
It's a total double-edged sword. You need the class score to figure out which query should handle the cat. But by relying on it, you allow the confident idiot to win the match sometimes.
And Stable Dino just resolves that tension. It says, fine, use the class score for matching, we still need it, but we're going to strip it of its independence.
By modulating it with the IOU.
You make it safe to use.
It also feels like it's bringing DETR back towards the philosophy of traditional detectors. I mean, in faster RCNN or YOLO, there's a hard rule. If your IOU is below a certain threshold, you are a negative sample, period.
That's a great point.
You don't get to be a positive just because you're really confident.
That's right. Stable Dino is sort of re-injecting that inductive bias for geometry back into the transformer world. It's making the argument that position is king.
And semantic confidence has to follow spatial reality.
It's secondary, yes.
So this makes me wonder about future work. They explicitly note that they only changed the classification branch, the box regression loss itself, the L1 and Jiayu loss. That's all identical to standard Dino.
That's the really provocative thought at the end. If this instability was holding back the classification head this much, is there a similar hidden dynamic going on inside the regression head?
Like a conflict between, I don't know, optimizing for the center point versus optimizing for the box dimensions.
Maybe. Or think about 3D detection. The paper points to this. In 3D, position is so much more complicated. You've got depth, you have rotation on multiple axes, you have velocity.
The whole idea of an overlap metric in 3D is so much harder to get right.
It is. And if you have a model that's super confident, it sees a car, but it's off on the depth by 5 meters, In a 3D context, that's a catastrophic failure. That's a collision.
So applying this stable philosophy to 3D forcing all confidence to be strictly tied to, say, depth accuracy or 3D IOU, that could be an even bigger win.
I think it could. The potential for the model to hallucinate or misjudge spatial relationships is just so much higher in 3D. Using these stable matching principles to constrain it seems like a very powerful, very logical next step.
It really feels like we're seeing the field mature. For a few years it was all, how do we just make transformers work for vision? And now we're at, okay, how do we optimize them correctly?
We're shifting from architecture engineering more towards optimization engineering.
Yeah.
We have the raw power, the models are enormous. Now we need the discipline to train them properly. And Stable Dino is a perfect example of that discipline.
So for a practitioner listening right now, maybe they're training a custom model on aerial imagery or something. What's the takeaway? Is this something they should go and implement?
Oh, I'd say absolutely. The complexity is really low. You're just modifying your loss class and your matcher class. You're not re-architecting your whole model.
And the dense memory fusion part is a very lightweight add-on.
A cheap way to get faster convergence.
Yeah.
If you can get state-of-the-art performance faster with zero extra inference cost, it's a no-brainer.
And even just as a diagnostic, if you're looking at your loss curves and you see them oscillating, or you check your false positives and find a ton of high confidence, low IOU boxes.
You know exactly what's happening. You've got a multi-optimization path problem. The confident idiot is winning the argument.
Don't let the confident idiot win.
That's good advice for machine learning and maybe for life.
Absolutely.
Yeah.
Stable Dino just gives us a blueprint for how to align a model's incentives. It's a great reminder that loss functions aren't just math. They're the instructions we give our models. And if those instructions are ambiguous, the result is going to be unstable.
Well said. Clearer instructions, better learning.
And we'll leave it there for this deep dive. Thanks for listening.